everyone. This week's episode is going to be a rebroadcast. This episode is all about color and what color even is, and then also how bleach takes that color away. And I'm really excited to be sharing this episode with you again 2 years after we released it for the first time.
This was really cool for a number of reasons, but one of them is also just that it connects to 2 recent episodes that we've done that are new episodes. So it connects to last week's episode about how denim is dyed and indigo dye and all that kind of stuff. And also a few weeks before that, when we talked about benzoyl peroxide and how that works to fight acne, it actually connects to both of those episodes. So a really cool episode to revisit or to hear for the first time if you hadn't listened to it before.
So we hope you all enjoy this week's rebroadcast, and we'll see you next week with a brand new episode. Hey, I'm Melissa.
And I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life,
the podcast that helps you understand the chemistry of your everyday life.
Jam, how are you doing on this lovely February afternoon?
I'm doing very well. It's a little cold up in here, over in the Texas area.
It's crisp and cool. We got a blanket of snow last night.
Yeah, just a little
a light throw blanket.
Yeah, light powdering of snow. Smattering, if you will. A sprinkle, a pinch. I don't know.
And now we're here cozy in the office recording. Before we get started today, I do want to say that I got this suggestion from a listener, from Mason K. So thanks, Mason, for all your help in coming up with today's episode topic. Are you ready to learn about what you're going to learn about this week?
I'm very ready to learn about what I'm going to learn about this week.
Learn about learning?
Yeah.
We're going to talk about how bleach takes the color out of things.
No way.
Yeah, dude.
Wasn't there a time that this got sort of mentioned, but you were like, that's for a future episode?
Yes, there was. We talked about this on the antioxidants episode.
Oh,
what
yeah.
are antioxidants and are they even good for you? And we talked about how hydrogen peroxide can decolorize the things. And this is not wildly different, but it is slightly different. And this time we're going to dig more into to learn about how to decolorize. First, we're going to learn about how to colorize. What are colors?
What are colors? So why does something have a color? And then we can learn about how it can be taken away.
Exactly. That's exactly right.
Interesting. I'm very ready for this. I've been around bleach a lot. I have used bleach in the traditional way, like laundry and stuff like that. But also in my pool store days, was around a lot of chemicals that had bleaching properties. A ton. So basically I had shirts that got little speckles of bleachedness in them. Had some shorts that got like a whole section of them that just became a different color kind of. So I've been on the receiving end of some bleach effects before. So
this isn't related to bleach, but acid can get on your clothes and eat away at the fibers. And then when you wash it in water, it's like enough of like the physical action to actually break the fibers up, so the acid weakens it, and then the washing finally ruins it. And I know someone who had been helping a student, got acid all over his shirt, didn't realize it, went home, washed it, put it on, and then realized there was just holes all over his stomach. I mean, it was ruined. Okay, so let's talk about the things that are responsible for color as we perceive it.
Okay.
There's 3 components, and we use these same 3 components when we're using instruments to detect color.
Okay.
So first, there's the light source.
Okay.
A light source is required for us to perceive color because essentially what we're seeing when we see color is light being absorbed and reflected.
Right.
Then we need to see the molecules themselves that are responsible for absorbing and reflecting the light. That's the second thing that's responsible for color. And the third thing is the detector, in this case, your eyeball.
Got it.
So that is the basics of science behind color, is you have to be able to shine light on something. You have to have a molecule that will absorb and reflect the color, and then you have to have something to detect color. So we have the light, the thing itself, and your eye. But today, for today's episode, we're going to focus on the thing itself, the molecule that makes up color. And the molecular structure behind it.
Okay.
Now, the type of molecule you have is very important. The thing that's colored. And we've talked about this in the past on the antioxidants episode.
Mm-hmm.
And we've talked about the electromagnetic spectrum several times. Do you want to give a quick overview of the electromagnetic spectrum?
Absolutely. Basically, it's the spectrum of waves and their frequencies from low to high. Mm-hmm. And so that includes things we cannot see, like infrared and microwaves and ultraviolet and all kinds of other ones, as well as the frequencies that we can see of light, visible light, Roy G. Biv.
Right.
So they're all part of the same spectrum.
Yes. And the first time we ever talked about that, I believe, was on the microwave episode. What the heck is going on inside of microwaves?
Yes.
So if you want a more thorough explanation, please go check out what the heck is going on inside of microwaves.
And then it played a big part in the rainbows. What was that one called? Yikes, we should know this stuff.
What do rainbows and mirages have in common?
Yes. And it played a big part in that episode too. We talked about it like quite a bit.
Yes.
So both those are good reviews for waves and electromagnetic spectrum stuff.
So, right, that was a great review of the electromagnetic spectrum. So you need light waves for that. Visible light shines onto an object, and what happens is when electrons absorb energy in the form of heat or light, they are excited and then they come back down almost instantly. The electrons go to a higher level of energy and then they release energy and come back down. So when they go to the higher level of energy, they're absorbing energy. And electrons can generally only absorb energy in certain increments. And so what we see when we're seeing color is an electron absorbing the energy in a certain region, and then the rest of the visible light is reflected back. So we see actually the complementary color of what's being absorbed. Interesting, right?
Yeah.
So, for example, the compound that's responsible for making carrots orange is called beta-carotene, and it actually absorbs in the 400 nanometer range, which is the blue-green range.
Right.
And that's why it reflects back the complementary color of orange.
Interesting. So white light is shining on it, like basically white, meaning like all the colors. It absorbs all of the green bluish light.
Right.
And then reflects to our eyeballs the orange.
Right.
Because it's complementary.
Yes.
Interesting.
And I don't know a ton about why it is like that. There's more that we're going to talk about the chemistry behind why it absorbs where it absorbs, but I don't know why it is that we see the reflected back color. So if there's someone who studied art.
Yeah.
And you want to dig into this intersection between art and chemistry, or if there's someone who understands more about optometry and how our eyes perceive, that would be great. So that's the basics of color.
Okay. So color is, oh man. So the building blocks of color are first that we have to have like the right things present, such as a light source.
Right.
A thing to absorb or reflect the light, whatever object you're looking at. And then the thing to be like detecting what light is doing after it reflects or absorbed off the object, our eyeballs.
Right.
Or in the computer situation, light source, object, and a sensor of some kind.
Right.
So those are the things you need first. And then
Yeah, because you can't see colors in the dark.
Right. Yep. It's one of those things I wish they could fix, but I don't know if I'll get there. And so objects at the like chemistry, molecular level, a lot of it has to do with electrons. And
as an organic chemist, I like to think everything is all about electrons.
Dang it. It's just like a Sunday school answer though. Electrons? You know, it's like true, but also too broad. I don't know. I'm stuck.
Electrons absorb light. in those special increments, remember?
So it depends on what like the makeup of the thing is and how many electrons it has.
Yes.
And the energy levels.
Yes.
Okay.
Every single thing. That's a broad statement, but I think, let's see how it plays out.
Okay.
Has electrons. All atoms made up of electrons.
Mm-hmm.
And so the electrons, when they absorb, not every single thing, but because if you lose your electrons, like a hydrogen atom, you're just a proton. But anyway, the electrons can absorb energy.
Yeah.
And they will always absorb energy in specific increments.
Okay.
And the increments in which they absorb energy, that is going to essentially determine if it's colorless or not.
Okay.
So this thing absorbs energy in a region that does not reflect color back, and that's why it's clear. This thing over here that's highly colored absorbs energy in the visible region.
Got it.
And that's why we see it as colored.
Yes.
So it's all about every electron can absorb energy and go to a higher level and then come back down, but it absorbs energy in specific increments.
And the carrot example you had is that it absorbed energy in the specific increment of like the blue-green, which meant that then it reflected the orange.
Right.
And that's why its increment of absorbing energy was in that region of visible light, of the blue-green. Okay, got it. Man, that's tough.
Now, do you remember what special characteristic things that generally absorb in the colored region have?
Highly colored stuff are the like antioxidants, where they have alternating double bonds.
Yes.
And that's why I think we even referenced that, like some fruits that are high in antioxidants in that episode, like strawberries or whatever, blueberries. It's like a related thing. It's not like it means, it's not like color equal antioxidants, but it's just like a visual hint. I don't know.
It kind of is. They have a shared property. Highly colored things have a lot of alternating double bonds. Those are what's called resonance. So the electrons are moving around. So that can neutralize the impact of a radical. But also it just naturally has the capability of absorbing in the visible region of light.
Got it.
So they go hand in hand. One doesn't necessarily cause the other, but highly colored compounds usually have a lot of alternating double bonds, and that characteristic of having a lot of alternating double bonds will then help diffuse the impact of a single electron.
Got it.
Okay. So you're with me.
This is hard. It's like it goes from, well, sort of. I mean, I feel like the part about, okay, light hitting this, absorbing this, some of it's absorbed, some of it's reflected. We have to have obviously an eyeball or like detecting thing of some kind to see it. And then it dives way in there and it's like electrons, energy levels. Like at the part that's relatable about our eyeballs and objects and light, it's like easy. It's like, that's our everyday.
You're like, I get it. There has to be a light switch turned on to see the colors of my room.
Yeah. But then it's like, goes so far in there. That's like very, very complicated.
Right. It is hard to think about describing why things have color without talking about their molecular properties. Things have color because of the way their electrons absorb light. That's the very, very basics of it. In a way, though, I mean, you know everything you need to know.
Okay.
That's a good explanation. We taught our OChem students learn this today in class about conjugated double bonds. That's alternating double bonds are called conjugated. They're in conjugation with each other. And how that relates to color and all of that. That's the basics that we teach in organic chemistry. And I don't know anyone outside of maybe color chemists who know a ton more about about the specific absorption of the electrons putting in the visible region. I'm not sure how much deeper there is to go. Anyway, that's the best I can explain it.
Okay.
But you need to know those basics. You need to know what I just described to be able to talk about bleach.
Okay.
So how bleach works is it is a strong oxidizing agent.
Okay.
Have you heard that phrase before, oxidizing agent?
Like OxyClean?
Oh yeah, OxyClean's a probably an oxidizing agent. I don't know off the top of my head.
I feel like they say something about oxidizing in the ads or whatever.
An oxidizing agent means that it removes electrons. If you ever took organic or if you ever took general chemistry, you probably had to learn oil rig. Oxidation is losing electrons. Reduction is gaining. There's also Leo-Ger, losing electrons, oxidation, gaining electrons, reduction.
Interesting. Yeah.
And another way to think about oxidation, though, is increasing the number of bonds to oxygen. That has the same general idea. We literally just have been going over this in my organic chemistry class. So this is things that students learn about oxidizing agents and reducing agents.
Okay.
So bleach is a very powerful oxidizing agent. It will add oxygen bonds, and actually bleach is oxygen and chlorine. It's made up of both. It's sodium hypochlorite is what it is, NaOCl, I believe. So it will add a bond to an oxygen and possibly a bond to chlorine, both of them. And when it's adding those bonds, it's breaking the double bond. So it breaks one bond to be able to form another bond, which interrupts the series of alternating double bonds, which therefore destroys the color.
Wow.
Because if you interrupt the stream of alternating double bonds, then you're interrupting the sort of highway these electrons were freely moving about. And because you've changed the way the electrons can move, you've now changed the way they can absorb energy.
Got it.
So they can't absorb energy in the same way. And if they can't absorb energy in the same way, they're not going to be the same color. Because absorbing energy is all about how they reflect color.
Wow. What the heck?
I wish you guys could see Jim's face. He really looks, his eyes are kind of squinty and he's looking off to the side and his head is tilted and he's thinking, he's just saying, wow, and shaking his head slightly.
It just is weird.
Unbelievable.
I think it's just, I had it in my head that bleach was so much washing the color out, which like is a very non-chemical way of saying a thing. Like, it's the same thought we have about like, you know, trying to clean something or whatever with. Right. It is chemical at the molecular level. We have a way of thinking about it because it's a daily thing that we do. The idea of it getting in there and interrupting like bonds and stuff, and doing it at this very, very, very microscopic level. Right. Is crazy to me. It just seems like, it's just never what I expected. I don't know. It just changes the structure of the molecules. Yeah. So when we talked about soap just removes the molecules and removes the dirt and washes them away, makes it to where they can be washed away. That was the very first episode, that one on soap. But this, you're removing a stain or a color or a dye or whatever by interrupting the structure of the thing itself and changing it. Yeah. And a byproduct of that can be that it's actually easier to be removed and washed away because it has oxygens, which can take part in hydrogen bonding with the water, all the things we've already talked about. Yes. But that is not the thing that decolorizes from bleach. It is the changing of the molecule itself. Gosh. It's a chemical reaction. Yeah. Yeah. Man, that's crazy. So that's it. That's how bleach bleaches. That's how bleach bleaches. Okay. Whew. Here we go. I'm going to take a crack at this. Okay, I am so ready for you to take a crack. I don't know why this feels a little harder for me. Like I'm having just a little bit harder time wrapping my mind around it. I don't know why. That's so interesting. Maybe I didn't do a good job as explaining. I did not sleep as much as I normally do. That I would not. That's not my feeling at the moment. I don't think it has anything to do with teaching. It might just be that some things are harder for me to understand than others. That's probably true. So, so we already talked about what it is that makes something have a color. Right. The electrons of an object that make up the object have an amount of the molecules. Make up the molecules. Could be all kinds of molecules, I guess, in one object, depending on what it is. Have an amount of energy that they can absorb. Right. So some of it's just a little bit. Some things can only accept a little bit. Some can a lot.
Right.
To the point of being able to be in the range of visible light.
Right.
That like electromagnetic spectrum. Enough to where it's in the visible light section.
Right. No more, no less.
No more, no less.
Mm-hmm.
So whenever light shines on it, it absorbs some of that energy and then reflects, or what do we say about that?
Yeah,
Reflect is kind of the word.
Yeah. That's something that I don't quite understand because it's not the same reflecting. It's not as if necessarily the light's shining back, but
not like a mirror.
That is the exact language that was used in, I found this old paper about the color of chemistry, and that is the exact language that they used in that paper, is that it's what reflects back. So there may be some updated information, although I couldn't find that. So if there's a color chemist out there or an artist,
Dude, a color chemist. What a cool title that is.
Oh yeah, there was 2 of the resources I used this week were by the same lady, the OG color chemist, from what I could tell, named Mary Virginia Orna. So Mary, Dr. Orna, if you want to reach out and teach us about why it's the reflecting, that would be baller.
Yes, please do. So it's absorbing a certain amount of energy.
Right.
And then reflecting light to our eyeballs.
Yes.
We talked about with the carrot in the carrot case of 2020. It is absorbing the energy level of light of the complementary color to orange.
Right.
Which means it then reflects orange.
Right.
So whenever white light shown on it, it's absorbing the energy level of the green blue light. And then so kind of almost taking that away. We don't see it.
Right.
And then reflecting orange, which is the complementary color on the wheel.
Right.
Color wheel. Or whatever. Okay. So that's light, that's color. And then to take color away using something like bleach, bleach has a lot of oxidizing.
It's a strong oxidizing agent.
Oxidizing agent. It does have oxygen in it.
It has oxygen in it, and it reacts very strongly.
Okay.
It is a very reactive species. It's not incredibly stable.
Yeah. It's got a lot of issues. Let's just say it that way. Yikes. So when you introduce bleach to something that has a color, it starts oxidizing and breaking up the electron makeup of something.
Yes.
And so say it has the alternating double bonds, like a lot of brightly colored things like antioxidants and stuff like that.
Right.
It starts breaking up that makeup, which changes the amount of energy it can absorb.
Right.
Which then can move it down to where it won't reach the visible light region in terms of reflecting light.
Yeah. I'm not sure when you say move it down, it's more like it just changes the light it can absorb.
Would it decrease it though? I mean, like decrease the energy it can absorb? Or is that not right?
I'm not sure. I don't know exactly how that corresponds to the amount of energy it can absorb. It just changes it.
It changes it.
I don't know off the top of my head. Maybe I should. If greater electron energy transitions are smaller or correspond to different transitions of the electromagnetic spectrum, I know that I have that in my brain, but I can't pull it out at this exact moment. So I can't say off the top of my head. I can't confirm up or down.
So it changes it.
It changes it.
And in most cases with bleach, it just turns it white or close to white.
It destroys the color compounds.
Man. And then we get heartbreaking situations like our favorite hoodie gets some white spots on it or whatever.
Or delightful situations like when our white kitchen towels got blueberry juice all over them.
Oh, yeah.
It's gone.
Yep.
The bleach takes care of business.
Yeah.
And it can react not only with color molecules, but also with odor molecules, which is why it can take the smell out of things.
Nice.
It's a chemical reaction. It's changing the
molecules. It smells pretty
molecules.
good. I mean, as long as it's not too strong, it smells very, very clean.
I hate the smell of bleach.
Really?
I do clean out my clothes washer with bleach occasionally because our washer just has, some washers just have the tendency to get that weird mildew smell almost. And I think ours has that. So to keep that at bay, I run a little bit of bleach through it.
Is it front load or top load?
top load.
Okay. Front load have even more tendency to do that.
Yikes.
Yeah.
Well, I'm going to give you a fun fact now that you've explained it back to me effectively.
Okay, wait, let me do this real quick, just in case. This one's a hard one for me. So listeners out there, if my like re-saying of the lesson was not as helpful as I typically try to make it be, I'm very sorry. This one was hard for me.
I think that's good for some things to be hard.
Yes.
And if I didn't do a great job of explaining, if you guys have more questions, if you need some clarity, we are here for you. So shoot us an email or a message on Instagram or whatever, and we will do our absolute best to clarify whatever we can for you that is confusing.
And maybe it just makes sense. Maybe it's like we're running into topics here and there that are just going to be much harder to put into different language.
Right.
It's going to require a lot of chemistry-y language, not as easy to put in every day. Because that's what I had a hard time with this. I was like, I wasn't able to find like no analogies came to mind.
Yeah.
No like regular folk kind of language that I use every day came to mind. It was like all in the chemistry sphere.
Yeah, there isn't a lot of non-chemist things that kind of correspond to when you break this up, it doesn't have its color anymore.
Yeah.
Or this pattern is what causes it to have color. I mean, there's nothing like...
And energy absorption and stuff like that. Like there's not like, what am I even going to use to like be an analogy for this that actually works?
The very, 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 very simplest way to put it is alternating double bonds make things have color, and you destroy that color by breaking up those alternating double bonds. But there's so many why with oxidation and bleach. But there's so many why questions. Why do those give color? Well, I wanted to answer that first. And why does the breaking up change the color, the way the color is perceived? You know, so there's like so many whys.
Why did it have to happen to this hoodie of mine? Is a question I have. And what am I going to do now? I just spent money on this hoodie and it happened in the first week. Why
is my life so hard?
Yeah. Why? Questions like that we all have. We hear you.
Well, now that you've explained it back to me.
Yes.
And I know you know, I'm going to tell you about a crazy thing called chloracne.
Whoa.
I know. It's crazy. So
Chloracne. Is it a type of acne?
It's a type of acne.
Whoa.
It's a type of acne that can come as, I mean, it's not really acne, but it's a skin condition that can hit you as a result of ingesting chlorinated compounds that can come from using a lot of chlorinated bleaches. So it's not like normal acne. It's a severe skin disease with lesions on this, like actual lesions appear on your face and your upper body. And it's as a result of ingesting or breathing in a high amount of what's called dioxins.
Gosh.
Dioxins are just a bunch of different types of compounds that have chlorine in them, and they just don't get broken down in the food chain. So they go out into the environment, and then they get put into the food chain by smaller creatures eating them, maybe even being in plants. And then they eat them, and the bigger creatures eat them, and they accumulate the amount of dioxins in their body. And then if we eat something with a lot of dioxins in them, then we can get chloracne.
What the heck?
Yeah. So ideally, you would minimize your use of chlorine-based bleaches. Okay. So something that would be better would be any bleach or strong detergent that says chlorine-free. So actually, I think OxyClean might be chlorine-free. Hydrogen peroxide we talked about how that also bleaches in the antioxidants episode.
Yeah.
But that can also be a good disinfectant agent instead of chlorine-based bleaches. All those types of products are going to be good for you. Anything that is chlorine-free but still cleans for you is going to be a better option than chlorine-based bleaches.
Nice.
So that's a fun fact before we wrap up with our week.
That's crazy that it can have that kind of effect on your skin.
Yeah, I don't know. And if there are environmental scientists out there who can teach me more, I don't know a ton about how the dioxins and chlorinated compounds, chlorinated just means chlorine containing, get into nature and what organisms in the food chain are absorbing or eating it. But I do know that we want to minimize our use of chlorine-based bleaches as much as possible. So,
interesting. That's good to know.
I thought it was a fun fact. And don't look up chloracne because it is brutal.
Oof.
Unless you just really like gross, awful things.
Yeah, fair warning. Don't do that.
It made me go, ooh.
I probably would have if you hadn't said that.
Yeah, not worth it. Just looks like, just imagine really bad blackheads. But I'm sure it's way more painful and it's way grosser to look at than that.
Yikes.
Okay, so great. So those are my lessons for you on chlorine, fun facts, and information about color.
Nice.
Thanks so much for coming to my office and learning all about bleach and colors today, even though it was a little hard.
Anytime. Thanks for bearing with me, even though it was hard for me to get.
And thanks so much to the listeners also for learning and listening and bearing with us.
Yes.
In our learning and our growing pains. Well, what's something good that happened in your week this week?
Something that was really cool about this past week is we had a Super Bowl gathering at my house. And it's not in the way that you think.
Yeah, don't get excited, listeners.
Soup or bowl. SOUPER bowl. And had nothing to do with the game. I think weirdly happened on the same day. Such a strange coincidence. And we had people just bring soups and soup sides and goods and whatnot. And about 16 or so people total. And like 6 soups, I think. So a lot of friends were there, which was awesome. Melissa included and her dude were there, which is really cool. And it was a lot of fun. We ate soup, didn't talk about football. And
it was a lot of fun. Yeah.
Enjoyed each other's company, and it was just fun. So that was a huge highlight of my week. Really enjoyed getting to do that with everybody.
Also, my roommate came.
Oh, yeah.
Both of my roommates.
Yes.
And the husband of the couple I live with made chili, and I know it's just a recipe that he's Googled on the internet.
Uh-huh.
And he won't tell me the recipe, yeah. But it is some of the best chili I've had. It drives me insane that he won't just tell me what the recipe is.
Yeah, it's so funny that he won't tell you what the recipe is.
It's not a family recipe.
Yeah.
It's one he found online.
I know, it's so funny they won't tell you about the recipe.
It's not funny. It's maddening. Anyway, it was a great time. That was a really good part of my week also, but now I get to do too because you already shared that.
Yeah, that's true.
I think my happy thing for this week that I'm so excited about was the snow. I thought I was going to be in Houston during that time and that I was going to miss the snow day. And then we, just due to a weird chain of events, I ended up coming home almost immediately. And then I thought, because I'm going to be here, it definitely won't snow. If I had been trying to drive back in this weather, it would have snowed, but it's not going to snow because I'm safely back in the Metroplex. And I got to see it snow while I was working on my homework. And it was just, it just made my heart so happy. I just really love snow. So that was nice. And I think a fun little gift from the weather. So that was awesome. That was a really cheery thing for me this week.
Yeah, that's cool.
Well, anyways, thank you guys so much for listening and for giving so many cool episode suggestions. We really appreciate you so much more than you know. This podcast has become one of the bright spots in both of our lives. So
absolutely. Melissa and I have a lot more ideas of topics of chemistry in everyday life, but we want to hear from you. So if you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, and Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share thoughts and ideas. If you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people. If you'd like to help us keep our show going and contribute to the cost of making it, go to ko-fi.com/chem4yourlife and donate the cost of a cup of coffee.
This episode of Chemistry for Your Life was created by Melissa Collini and Jerem Robinson. References for this episode can be found in our show notes or on our website. Jerem Robinson is our producer, and we'd like to give a special thanks to A. Hefner and V. Garza, who reviewed this episode.